So acceleration is like velocity. I'm reminding you, what kind of quantity is it? Really? Think, Cole. Come on. Do you remember the difference between a scalar and a vector? Little review from first unit. Acceleration is like velocity. What kind of quantity? And of course, everyone said, oh. It's a vector. What makes it a vector? Remember the villain from Despicable Me? Committing crimes with both magnitude and direction. Acceleration has direction. Up, down, left, right, north, south, what have you. Okay, so now that we know that it's a vector, it can be positive. Which direction is positive? Know this one? Not the backwards one when you're up here doing the cards, Graham. Remember? I had to think backwards.
I think that tomorrow for class we should watch this thing. We just so that was really grow an understanding of what vectors are.
Yeah. Just for that 20-second scene, right?
No, the whole class.
Oh, the entire class.
Just for the 20 seconds.
Yeah. Only if you promise to laugh during that part. Oh, Peter, you remembered your number. Good. Can be positive, which is? Please tell. True answers. Oh, Mr. Bennett. True answers. I know. I'm such a terrible person.
I can't affect my average now.
Positive can mean to the right. Watch your language, RY. To the right, and it can mean up. Now, could it mean down? Sure. If you define down to be positive, you go right ahead. You'll just be, the only person in the world that does that. Positive, right, and up. Yeah, but this is going to affect your average positively because you know you're going to get the next one right, aren't you? Right? You're going to get this one right, aren't you? Everyone? Yes, it will. Try it. Negative acceleration. Now we have to start being careful here. Or AD. Yes, negative, up and down, right?
When you say to the, you can't say to the down. So it should
No, you can't say to the down.
You're wrong.
My grammar is wrong, my math is correct. Now, does deceleration always mean slowing down? You're not going to like how this goes, but this just cues me into a little conversation. So take a guess, because that's what it really boils down to here. Does deceleration always mean slowing down?
Which one's A or B?
There's a Y and N button on your clicker. Does deceleration always mean slowing down?
Where's the Y?
Oh, we do.
Oh, yeah.
Right at the top there.
True, false, yes, no.
Willie, do you have a clicker there?
No.
What do you think? Graham's going to be last.
No. Oh.
Oh, yeah.
Now, this isn't entirely true. The only reason I ask this question is I want to have this conversation. Now, there's obviously some fine print right here. Can you guys read that? Pretend you're at the optometrist. Read the bottom line. Acceleration to the left is sometimes called deceleration. But be careful, it doesn't always mean slowing down, because if you're already moving, if I'm already moving left, and I'm accelerating left, then I'm going to be doing what?
Going left.
Speeding up to the left. Okay? So I would strongly suggest, here's a little picture here that might help explain. Right? if you're moving to the left with a velocity of -5 and you're accelerating at -2 meters per second squared, decelerating, then you're actually going to be speeding up to the left. All I'm saying is, really, this word is a dangerous word because it has sort of double meaning. Okay? Negative acceleration, you have to be careful with because people assume that means that it's slowing down, but it doesn't. If the speed is already negative, while we're moving to the left, then the object could be speeding up. And more on that in a bit. All I'm really saying is be careful about the word deceleration. Now, if you had to define it, if I said write this down because this is important, that would be your definition of acceleration. It's not particularly easy to understand. And I believe this, acceleration, you probably all have a pretty good idea of what acceleration means, but I'm guessing you really don't have a true understanding of the mathematics behind it. So that's today's sort of job, is to come up with that. Increase your understanding of acceleration. So acceleration is the time rate of change in velocity. And I'm going to give you a couple of alternate definitions right away as well. And as always, feel free to write anything you want down. Although I always encourage you never to write every single word. This will all be posted later. If you want to sit back and just soak it all in, I'm good with that too. So acceleration is the time rate of change in velocity. It's the rate at which velocity changes. Now, velocity, like Despicable Me, is a vector, which means it has direction and magnitude. So you can change the magnitude of the velocity, which means changing the speed, but it could also mean changing your... No, it is more. It could also mean changing your direction. When you change direction, you are accelerating. How fast you change direction is your acceleration. I'll give you an example. I need a tennis ball. Okay, when I drop the tennis ball on a table, it speeds up, has an acceleration. Anyone know what that acceleration is as it falls to the tabletop? What the number is? Sorry? 9.8. 9.8 meters per second squared, right? As it falls. Now, when it hits the table, does it slow down? Sure, and if you had like a high-speed camera, you would see the tennis ball actually do what? Like it would compress, right? And then it would expand, and then it would bounce back up, right? If I drop a marble, is that going to compress and bounce back up? It's not going to bounce up? It does not, right? Not quite as much? Actually about the same, right? One compresses and one doesn't. Is it accelerating when it's in contact with the table? No. No?
Yeah, because it's compressing.
Because what? Yeah, but one compresses and one doesn't, but they both change direction, don't they? So they're both accelerating, but are they accelerating at the same rate?
No.
Why do you... You're always quick with the answer, Paul, and then I look at you and then you switch your answer. You should learn. Why do you say no, my friend? I don't even remember what the question was. What did I ask? Oh, is it different? Yeah, is it? Are they? I think I said, are they accelerating at the same rate? You said no before I even finished my question. No. Why do you think? Which one do you think is accelerating greater? Really?
No,
This one? Why this one, Greg?
Because it's hard.
They're kind of both the same. Actually.
Smaller.
Smaller?
The marble is going to accelerate faster because it doesn't compress as more, and so the force is going to take down.
Okay, so why is talking about the time? How much time are they interacting with the table? Which one is longer? A longer amount of time? Tennis ball. How come? Because it compresses, right? Longer period of time, really short period of time. Boom, right back up. Which one has greater acceleration?
Marble.
Mark. Greater acceleration. Because it changes its speed,
Quicker.
changes its direction, what?
Quicker.
Quicker, very good. That was fun.
I want to call.
Did you?
Yeah.
Acceleration is the time rate of change of velocity, or how fast an object's velocity is changing. How fast an object's velocity is changing. Or how fast is an object's velocity increasing or decreasing. Either one of those is acceptable. Right? I'm trying to get you multiple definitions of what acceleration means. Generally, when I ask, if I were to go into a class where grade 9s and ask them what is acceleration, what would they likely say?
Speeding up.
Speeding up. Something is accelerating, that means speeding up, right? And are they right?
Yeah.
Well,
Partially.
partially, right? It's the whole idea of expanding your knowledge and expanding that model of understanding. So it could be speeding up or it could be slowing down, but again, it's the rate, it's the rate at which the velocity is changing. If Cole's playing baseball, he's playing shortstop. Play baseball, right? No? Shortstop?
You're filling up the water bottles at this rate.
Okay, so Cole is playing baseball and he's filling up the water bottles at a very fast rate. Okay, never mind. Jake, shortstop?
Sure.
Okay, thank you. Okay, so Jake's playing shortstop, right? And there's a hard grounder hit right at him, right?
Goes through his legs. Every time.
Every time?
Every time.
How come you're not playing in this spot then?
Oh, maybe I can't
Was that
hear
your
you.
water
Yeah,
bottle's
someone's
up?
Maybe he's thirsty. The water bottle's empty.
Someone's gotta warm the bench here, Cole.
I can't hear your voice.
I was a pretty good bench warmer too, Cole. Okay, so anyways, he gets down, right? And when that ball comes fast, what does he do with his hands?
He probably goes like that.
Yeah, and then what are you supposed to do as you ground it? You're supposed to absorb it. How come? It's so that it increases the length of time so that there's a smaller acceleration and not as much force, right?
Yeah.
If you like run into the wall and don't slow down at all, right, it's going to hurt, right? But if you sort of give with it a little bit, right, if you sort of, it's not going to be so bad, you're going to slow down at a greater rate. If I smack you like that and you roll with the punch, is it going to hurt as much?
Yeah. Still gonna hurt.
It's going to hurt me, right? You can go ahead and say that. Yeah, if I smack him one and he rolls with the punch, if his face is in contact with my fist for a longer period of time, it's going to hurt less. When you are swinging the baseball bat, when you get that one at bat, because you're up 9-1, right? You get that at bat?
Sometimes.
Should you follow through when you swing? Really? You just maybe that's why you're not getting many at bats. If you follow through, the bat will be in contact with the ball for a longer period of time, which actually increases the force and it goes further. Okay? All things to think about. Actually, that's a kind of a grade 12 thing. I'll get to that. I sort of went farther than I usually do. If you want to really boil it down to basic whatever, how fast you get to how fast you're going. How fast you get to how fast you are going. If you get on your dirt bike and you pin it, how fast do you get to top speed? Dylan, dirt bike? No? Who's got a dirt bike? Graham, dirt bike? Yeah, Lane? Okay, Lane. What kind of dirt bike you got, Lane?
Nothing right now.
Oh. Okay,
Yeah, I got you.
okay, so you get on it and you pin it, right?
Yeah.
What's top speed on the dirt bike, roughly? 110 kilometers an hour? Okay, how fast can you get up to 110? 5 seconds? Okay, 5 seconds. Okay, I get on my pedal bike, and I'm old and I'm out of shape. My exercise regime has consisted of changing the channel in the last couple of years. I get on my pedal bike. Can I get up to 110 kilometers an hour? Well, if I went up to the park on that big hill and someone pushed me, it would be scary. I don't even like doing it in a car. But could I get up to 110?
Probably.
Yeah.
Maybe that big hill like on the way to Mendoza, right? That's a big hill.
If someone's like pulling you behind the wheel,
Okay, fair enough. Let's go with that, right? How fast, even if I get up, if I'm pedaling as fast as I can and Lane's on his dirt bike and we're going down that hill, who's getting up to 110 faster? He's got a greater acceleration. I can get up to the same speed, just takes me a whole lot longer. Even if I had a dirt bike, I wouldn't get up to 110 that fast because I'd be afraid. Okay, my friends. After all that, now I got to give you the formula. Now you're going to have to think here because I've talked about acceleration being the change in velocity.
Huh.
I gave you a hint.
It's either CD.
Fine. Let's see if we can get it right. Well, then we're both right.
What is it?
Change in velocity.
Wyatt.
Enter Wyatt.
So Wyatt.
And usually, I get a bunch of people all across the world. Oh, I'm glad to see no one picked B. Excellent. The correct answer is D, and in fact, the majority of you got that right. Well done. Why is it D?
Because we just took notes off.
Did we really?
Yeah.
We didn't write that formula down, did we?
It says time rate of change velocity.
Well, I didn't, but I never gave you the formula until now, did I?
No, that's
Yeah. Okay, so good. So why is it D? Because, well, they're all over T, right? Okay, let's just go through them. What does delta D mean? Displacement, change in position. Not that one. Not change in position. What does D bar mean? Average position. V bar. Average velocity. I am so glad that, how many people pick C? A few. Okay. Mr. Smigowski, I'm putting you on the spot. True or false? Don't give me any unless nonsense. False. You don't know how many times I've had to write that on tests. Because even grade 12 still get it wrong. What do those things mean? I want to roll here, Mr. Smigowski. Give me 3 seconds. What do those two things mean? Delta V, what does it mean? Change in velocity. What does V bar mean? Average. Are they the same? No, they never are. If I got 50% on my first test, sad face, and I got that's a bad one. Let's go with 90% on my next test, smiley face. What is my change? How much did my mark change by? Graham's mark went down from 50. Your change was plus 40. What is your average? 70. Are they the same? No! And I'm going to rant and rave, and you're still going to do it wrong on the test. And I think some people do it just to annoy me, Wayne. What can I do for you, Mr. Smigowski? Does that make sense to you? Change average. Different, right? Please tell me you're going to get that right.
I'm probably gonna get it wrong.
I know. Okay, so there is the formula for acceleration. Change in velocity over the change in time. If you want to write it out in words, there it is. Acceleration is the change in velocity over the change in time. Keeping in mind that changing velocity can mean changing direction. Can you give me an example of an object, whatever it might be, marble, tennis ball, laying on a dirt bike, where the speed remains the same, but the direction changes? Is that even possible? Exactly. St. Rose Corner, right? You got it on cruise at 99 because you don't want to go 100, and you don't take it off. You just go around that corner, and your speed changes. No, it doesn't. Only the direction. Very possible. And we'll get into the direction of the acceleration at a future time. Okay. In the graph below, the displacement graph, now by the way, I should have told you this. I have all the graphs if you want. I'm going to hand them out. What I did in the past, many years ago, and when I wasn't such a great teacher, I would make people write notes, and I would say, okay, you can draw the picture, or you can kind of do what you want, right? So I'm going to hand this out. You can do whatever you want with this. Okay? If you want to leave a space and cut it out, if you're madly trying to write notes down, you want to throw these in. If you want to write notes on the side of this, that's fine too. You want to hand in quizzes from like last week, that'd be good too. Okay, so back to the graph at hand. Did I get everyone? Sometimes I miss people in the middle. In the graph below, this is a displacement graph. Remember the lab we did the last 2 days? Does that look familiar? I hope so.
No.
Meaning that the velocity is... Which one is it? Did you answer?
It says changing.
Yeah, we can read it.
Slope is changing. That doesn't help.
No, it doesn't, does it? The velocity here is the velocity increasing, decreasing, increasing, or staying the same. The velocity, is it increasing, decreasing, or staying the same?
I don't know what this is.
Oh my god.
I just haven't experienced it.
Oh.
Okay.
I've heard C.
All good? All right. What is it?
Hey,
The velocity is increasing. Is that the graph you got when you rolled the ball down the ramp? I hope so. There was the odd group that had this. What was the problem when they did that? What did they have? What was the problem? You remember? You had the time and the thing reversed, right? Yeah. Okay, so it's increasing here.
No, I didn't.
The slope is changing, right? Here the slope, how would you describe the slope right there? Shallow, not so steep, steeper, steeper, steeper. The slope is increasing. Good. Okay. This is a challenge. Since the velocity is increasing at a constant rate, I'm going to tell you that. The velocity graph is a blank line as shown below. Which one of those three is the corresponding velocity time graph? Which one of those three is the corresponding velocity time graph? The graph of velocity. Huh. Remember when Graham did the cart thingy and he was moving it back and forth, right? I could have shown you velocity time graphs, but I didn't. But if I did, what would they look like? Think about it. You have the tools. I've given you what you need. It's can you apply it? It's okay to get it wrong here. We're learning. What say you, Cole? Are you ready? Feeling confident? Yay! Awesome, you guys. Why is it that one? Because the velocity, we already said it. The velocity is what? Increasing. The velocity is increasing, and I told you that it's at a constant rate. It's increasing. This is velocity time. Here the velocity is like 1, here the velocity is 2, here the velocity is 3. It's a graph, it's a velocity time graph of Lane going down the big hill on a dirt bike. If it was a graph of Lane and I on our dirt bikes, flat, I'm a scaredy cat, right? Identical dirt bikes. He's experienced, I am inexperienced. What would the difference in the graphs be?
You'd be going slower.
What would my graph look like?
This.
Like flatter?
More flat.
More flat. So like this would be like Lane like that, and I would be like that.
You just wouldn't be good.
It'd be flat.
Yeah, you'd be too scared.
Yeah, I'm not getting on a dirt bike with my concussion. I had a helmet on that day. The acceleration graph is a graph of the slope. It seems like I skipped something there. Okay, no, okay. All right, so if I were to graph the acceleration time graph from that, acceleration is the slope of the velocity time graph, what would it look like? Well, it would be flat. The acceleration graph is a graph of the slope of the velocity time graph. The slope of this graph would be 0.4. This means that the acceleration is a constant 0.4 meters per second squared, and we would call this uniformly accelerated motion. Again, what does the word uniform mean? When Cole is sitting on the bench filling the water bottles, he's wearing his, so he looks the same as the guys that get play. Sorry, Matt.
And with that stuff, we're getting into meters per second cube.
We'll get there. That's something else. This is uniformly accelerated motion, speeding up at a constant rate. Okay, and it's flat. This whole thing, you can, don't worry if you don't get that. What do you have to absolutely know? You need to know that that is increasing, and you should know that the velocity time graph is like that, and that the velocity is increasing. Okay. Another challenge here. Are you up for it? This velocity time graph, do you have it?
Yeah.
Yes, you do. It's on your little sheet thing there. So those of you that are writing absolutely nothing down, you have it to look at. The velocity time graph is an example of variable acceleration. Variable acceleration. What does that mean to you, variable acceleration? Peter, what do you think that means, variable acceleration?
Either.
What's all, like the acceleration's all over the place? Okay. So you're not speeding up at a constant rate or slowing down. It's kind of,
It varies.
yeah, jerky. And in fact, that's the proper word for it, is jerky, not beef jerky. The acceleration is not constant, or could be constant or not. What is the acceleration like? Again, be careful. This is a velocity time graph. This is a velocity time graph. And acceleration is the slope of the velocity time graph. Here I'm showing the slope. The acceleration is? Are you having trouble, paying attention for this long? Are you?
No.
Oh, you're good? You're still imagining yourself on that dirt bike giving her? The next time you get on your dirt bike, you know what you're going to say to yourself? I'm accelerating at 5 meters per second squared.
Probably not.
No? Come on, do it for me, would you? Not constant. The slope is never the same. The slope changes. Now, how would you, let's put Lenny back on the dirt bike, how would you describe, what would you be doing to create a velocity time graph like this? This is speeding up,
Yeah.
then this is slowing down, and then speeding up again. Maybe he sees like a, I don't know, something to cause him to slow down. Maybe, yeah. And then he should be speeding up a whole lot more. Okay. My friends, I love this question. Because if you know the answer to this, you're in good shape. And if you don't, that's okay, we just got work to do. But if you know this, and not just a guess, if you know this, no, not 50-50 guess, if you know why you're picking the answer and you get it right.
It's at the bottom.
Time is at the bottom. Does this object ever move backwards? Not back in time, backwards, like, backwards. To the left. Not an easy question. I know it's yes, no, and it's 50-50. But if you truly know why, you're in very good shape.
I would say.
Do I close my eyes?
No, don't think.
Oh, shit.
Yeah, it's gonna be.
Sweet, it won't work. There we go.
Well done.
Oh yeah.
Who knows why the answer is no?
He's
Because
moving
you
in
can't
a
go back
positive
in
direction.
time.
Why, Graham?
He's always moving to the right.
You're right. How do you know that? It's always moving to the right?
You can't go back.
Because it doesn't go into the negative. Very good.
Yeah.
The velocity never goes below zero. This just means positive velocity, moving to the right. Still moving to the right? Yes, just slower. Just slower. Right here the speed is 4 meters per second. Here the speed is only 2. Moving to the right but slower. Saw the grizzly bear but wisely kept moving. I don't remember how this goes. Draw a velocity time. I've changed my notes and I don't. Draw a velocity time graph with a similar shape that shows the object moving backwards. Oh, okay. So I want you to draw a graph, but it's got to be moving backwards. So it's going to be in the negative territory. And we want to show it speeding up, slowing down, and then speeding up again. What do you think? How would I draw it? Does anyone want to come try? No?
It'd just be a straight line.
Straight. It says with a similar shape, right? So like, I want to show speeding up, slowing down, speeding up. But backwards.
Do the same thing.
Speeding up, slowing down.
Go down. Yeah.
Like that? Yep. Velocity time graph, right? Speeding up, speed getting here is -1, -2, -3, right? Going faster, oh, going slower, oh, going faster, grizzly bear, let's go. Graham, you're looking for a picture of a grizzly bear or what?
Yeah.
I think I'm almost done. Let me see how many slides I got left here. Now, back to the original one. Notice that the slope of the curve is not always positive. Right? The slope here, slope positive or negative? Positive, 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 right at that peak right there. I would say flat 0, negative, negative, flat, positive, 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 right? Between points A and B, right here, what is the change in the velocity? I started at 4, I ended at 2. My change in velocity is -2, and my time, it took me 1, 2, 3 seconds. And so what is my average acceleration between points A and B? -2 divided by -3, and my average acceleration is -0.67 meters per second squared. My acceleration is -0.67. I'm slowing down at 0.67 meters per second every second. Every second. Every second I slow down by 0.67 meters per second. I know, I'm starting to wear out my welcome here, aren't I? Right? Are you mentally okay? I've had it. That 40 minutes, I'm done, right?
Yeah.
Would that be average acceleration?
That is average acceleration, right?
So there should be a bar on that.
Mm-hmm. Right, you are. Now, notice the units on the acceleration. Here's where I get into this bit here. Acceleration is the rate of change of velocity. It's the rate of change of velocity. And what is velocity? Velocity is the rate of change in displacement. Don't write anything down, just watch. Many of you are already doing that. That's okay. Acceleration is the change in velocity over the change in time, but what is change in velocity equal to? D over t. So I've really got d over t over t. D, if I use the units, what's d measured in? Meters, time is seconds, so it's meters per second per second. Here's the math. Meters per, don't write this down, meters per second per second. Remember how to divide fractions back in junior high? Meters, time, flip end, this is meters per second divided by seconds. So you flip the second one end, multiply. So instead of seconds over 1, it's 1 over seconds. And you multiply by multiplying across the top. So meters times 1 is meters, and second times second is meters per second squared. And that's where the units come from. Do you have to be able to do that on the test? Absolutely not. I'm not an idiot. I might. Don't. I just want some of you to see where the units come from. The units for acceleration are meters per second squared, or meters per second per second. I got a video for you because I know that you're ready to stop listening to me. This is my friend Galileo. He died a long time ago. He was the first scientist who clearly understand the concept of acceleration. The church didn't like Galileo, as you'll see in the video. They didn't like him doing experiments because he found out things that they didn't agree with, and so what they did was shut him up. They put him in jail. Unfortunately, it backfired because what it did was it gave him more time to do experiments. He found that the acceleration of a ball rolling down an inclined plane, just like you guys did Monday, and the acceleration of a falling object were both described by the same mathematical rules. You'll find in the video that he really wanted a tennis ball, and he wanted to graph how it fell. The problem was he lived in the 1600s. They didn't have tennis balls, and they didn't have slow-mo on their iPod, on their iPhones back then, right? All they had was one of those little hourglass things. Didn't work so good. So he had to come up with a way to slow this whole thing down. So how did he do it? He built a ramp like the ones you guys had, and he rolled it down. And he realized, oh, it's exactly the same, right? Because a ramp is really just like the rules for the ball and the ramp should be the same, whether it's like that, or 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 in fact, if it's, well, straight up and down. A straight up and down ramp is just free falling, right? Okay, so he said, hey, the math must be the same. I'm just going to slow it down. Now, he built giant ramps. Those are little boy ramps compared to the ones he had. He had one like the length of this room. They're going to show one. Okay? Did he have a stopwatch?
No.
iPhone? No. Would the hourglass timer thingy work? No. So what did he do? What did he use for a timer, do you think? The sun? It'd have to be a super long ramp to use the sun. He had to come up with some way that he could time. I'll give you a hint. It had nothing to do with seconds. There's actually I haven't been able to find out the actual truth because there's two different versions of the same story. I'll show you the video. Oh, I please hope it works. I hope